Welcome to the Argon Design High Frequency Trading demonstration. We are using an Arista network switch as a trading execution platform. We will show how the switch makes market orders based on market information with end-of-packet to end-of-packet response times of about 170 nanoseconds. The FX switch from Arista is unconventional because it contains an FPGA that has direct, hardware-level access to the last 8 of its 24 10 gigabit ports. We are currently using 2 of these ports. This slide shows our fast path approach to making market orders. The high-level trading algorithm does numerical analysis over global market activity. When a potential future opportunity is detected, the FPGA in the switch gets instructed by the trading algorithm to look for that opportunity. The opportunity is expressed as a trigger condition with a set of rules, which we will discuss later. The decoupling of the trading algorithm from the low-level order execution allows for market order response times from market information received in the critical path to be very close to the theoretical minimum. Here's an overview of our setup. At the bottom are the feed and exchange simulators. They connect through 10 gigabit ports to the switch. The switch is then connected to an x86 terminal, which acts as a gateway to configuring the triggers for sending market orders. In a real trading system, those triggers would be reconfigured in real time by a high-level trading algorithm, which would keep track of more global market tendencies. The first switch port is connected to a feed simulator which sends market updates. The second port is connected to an exchange simulator to which sell and buy orders can be made. In response to those market orders, the exchange simulator sends execution reports. In this Wireshark capture, we show the kind of traffic involved. In red are the communications on the feed port, which contain the market updates. In green are the communications on the exchange port, which contain the execution reports we receive and the market orders we send. This is the computer which has the feed and exchange simulators. This is the switch and the scope to make latency measurements. And this is our terminal where the strategy trigger conditions are manually entered and executed in real time. We use 2 techniques which are made possible with the use of an FPGA. The first technique is inline parsing and matching of the fixed messages. As the Ethernet frames enter the FPGA, the fixed key value pairs get parsed as soon as possible. This allows us to extract partial information from the Ethernet frame before even the whole frame has been received. The second technique is what we call preemption. Instead of waiting until the end of the fixed messages before acting upon them, we start sending the overhead part of the response, which contains the Ethernet, IP, TCP, and fixed headers. This allows us to finish sending a populated response right after a match is made. If a match is not made, we poison the Ethernet frame by using an invalid frame checksum. This aborted frame will be discarded by the network device at the other end of the cable. The latency from the end of packet of a critical fixed message to its corresponding market order response is roughly 170 nanoseconds. This includes the phi and MAC round-trip latency overhead of 150 nanoseconds. When preemption is disabled, the gap between the fixed message end of packet and the start of packet of the corresponding response is only 6.4 nanoseconds. But we then incur the full serialization delay of 150 nanoseconds to send the market order.
The incoming market data feed uses the fixed protocol, which is a series of key value pairs, e.g. price equals 1000, quantity equals 100. A real trading system may have multiple market feed ports, so for each port we define a set of trigger events, each with an associated action. Each trigger event is a set of key value rules, all of which are compared against the incoming market data by the strategy matcher, and must all be true for the order to be completed. These triggers will be updated in real time over PCIe or 10 gig Ethernet by the high-level trading algorithm running on an x86. However, for this demonstration we are manually changing the triggers via the configuration terminal to allow testing of specific cases. Any valid fixed key and ASCII value may be used, along with the conditions less than, greater than, equal or not equal. In this example test bench we have 4 rules which match any symbol and any price offer in a market data refresh, and our action is to buy 100 units immediately. Looking at the oscilloscope, we can see that the preempter's orders are sent without aborting, finishing 12 nanoseconds after the end of the feed packet. If we now change the price rule to only match values ending in less than 5, where extra notes don't care, 50% of the preempted orders are aborted by poisoning the frame check sequence, and we see ghosting between the two cases on the scope display. This is a very simplified demonstration. In a real trading platform, the FPGA could be programmed with modules to compute functions such as moving average or any other indicator metric. In a similar way to our updating the rule tables, the connection between these function modules and the strategy matcher could then be continuously reconfigured by the higher level trading algorithm in order to implement a long-term trading strategy. This FPGA approach then allows flexibility and scalability to be retained at the higher level, whilst reducing offer-to-order latency by a factor of 20 compared to software-only approaches.
Welcome to the Argon Design High Frequency Trading demonstration.